let's get this going. Just so you know, you're going to hear my wife singing my son to sleep in the background. But let's get this going. So, explain the membranes. Okay, so this is our lung, beautiful lung. We'll zoom in here. So we got a couple different layers here. First layer that we got is our lung in here. This is just the inside of this. We have our parietal pleura. This is attached to our ribs, and this is a stationary one. It doesn't move at all. We have our visceral pleura, and this visceral pleura is actually what moves. That movement makes this vacuum right here, and we're going to get a negative 3 millimeter of mercury and this negative 3 millimeters of mercury is when the lung is completely deflated. So after all the oxygen that you can't out is done. This is filled with serous fluid, and this fluid is pumped out via the lymphic system, and so it gets pumped out of the lymphic system, making it a negative value because it makes like this vacuum type pressure, I guess you can call it. So there's a few different types of cell that's within our lungs. The first type is type 1 alveolar cells. They're just simple squamous cells. It's about 95% of what we have, and the primary function is just simple gas exchange. We also have a secondary, or a type 2. This one is the pneumocytes. Basically, they produce surfactants, and surfactants is actually really cool. So surfactants, these are little alveoli here, or your alveoli, and there's water molecules all along this, and we've all taken enough chemistry to know what I'm drawing here. Unfortunately, we've all taken enough things. I'm just gonna make it my job easier, because you know what I'm drawing here. So I drew this side correctly, this side correctly, and this side incorrectly, but that's okay because you understand what I'm saying. Water wants to make hydrogen bonds because it can, and these sacs are really, really small, and so what happens is, filled with water, it's gonna want to make a little sac, and they're going to want a hydrogen bond. So this hydrogens want to come over here to bond that guy. That one wants to come over here for that guy, and we're going to start getting not on an oxygen. We're going to start wanting to get close to each other, and this is going to cause a collapse. So this is going to come in. What surfactant does, again, surfactant's made by those type 2 cells, and those type 2 cells are going to come, and it's got a hydrophobic end and a hydrophilic end, and it's going to make it where our lungs become more compliant, and it just makes it easier to open. So that's one thing that makes our lungs constantly want to collapse, is that water within here. The other thing that just wants to make it collapse is this pressure here. So this pressure is making this vacuum, and it's always wanting to kind of collapse in on itself. A pneumothorax is kind of interesting. A pneumothorax is when you get air within this, when there's a hole rupture, either a GSW, gunshot wound, stabbing, whatever it may be. You get air in here, and then your lungs will collapse. And when your lungs collapse, one thing that they can do is they can put a tube in here, and this little tube will let air escape out, and that can help restore this negative pressure that's in there. There's also something called a tension pneumothorax, is when you inspirate, more air comes in, and then when you try to exhale, no air can come out, and so there's a lot of tension, a lot of stress. There's also something called pleuritis, which is an infection or inflammation within your pleural space, which is in between your visceral pleura and your parietal pleura. and it's just this space right here, and it can cause a lot of pretty sad problems. And clinically, you can actually hear kind of a rubbing noise that it makes. It's kind of gross. But so we talked about negative pressure ventilation. Oh, negative pressure ventilation is kind of interesting. So negative pressure ventilation is mechanically, another name for it is mechanical. So when you, for example, what happens is they'll do like an intubation tube, and they'll hook that in. Oh, that was horrible. They'll do an inhalation tube, and this intubation tube is connected to O2, and we're going to force that in there. And so that's positive airway, or positive pressure ventilation. Negative pressure ventilation is kind of what we were just talking about. These values here, surfactant working, things like that, allowing our lungs to go. We talked about pneumothorax. We talked about surfactant. Lack of surfactant makes our lungs more compliant, so it makes it harder for our lungs to expand. And that's with surface tension. So we have this law. Let me see if I can find it on here. This law called no, it's somewhere right here. The textbook uses Laplace's name, and then also Place's, or however you say that. One of them starts with a P, one of them starts with an L, but they both have the same formula and same description. Anyways, whatever. So surface tension is what we were talking about with surfactant. So as we increase surfactant, we also increase surface tension decreases, which would decrease this. One of the biggest factors, and this is pressure, by the way. One of the biggest factors here is radius. Radius is a huge factor. And radius, because our lungs naturally want to collapse, we have a low radius, which means we need to really increase pressure in order to get anything going. So that's super, super important when we're looking at like fetal development in the fetuses. Babies don't need. There's a structure within the heart that allows blood to just kind of skip through the right ventricle and just head straight into the left ventricle. That's responsible with pumping blood systemically, because we get oxygen from our moms in utero. And so as a baby, we don't need, our lungs can be super, super compliant without it really being that big of a deal. However, when we come into this world, we really want lungs that can expand. And so, long story short, what happens is that during about 30 weeks of gestational development, the moms will start producing cortisol. This cortisol then makes surfactant. And so when the baby comes out at about 34, 35 weeks is when is the earliest babies can come out quite safely, because the lungs are completely developed with surfactant. So when they come out and they're having to take breaths on their own, it's not impossible. Now, if we think that a baby's going to come earlier than that, we can give steroids for it, and that can help a lot with being able to, for the baby to develop surfactants. That medicine is called, it's a steroid called cortisol. And so that's one thing. And if they don't get that, then that's when we need to use this positive ventilation, which is really just kind of sad. And so now let's look at how blood is transported within the blood, which is kind of really cool to me. I want to use this one right here. I wanted to draw on it with you. Okay, so what happens is we have this red blood cell. That's what this little guy is. So what happens is that diffusion will occur because of pressure gradients. So we have a low pressure gradients here, and we have a high pressure here. So what will happen is these particles are going to want to come in. When these particles come in, that's 2% of what it's needed. Because then those particles are going to move into here and they're going to bind to this hemoglobin. Hemoglobin can take 4 molecules of O2. So that's how oxygen is transported to the cells. Is it hops on a ride in the red blood cells within the hemoglobin, takes 4 of them. Now CO2 does something a little bit different. What happens with CO2 is that CO2, some of it, and I drew that down here, some of CO2 can bind to hemoglobin, only about 2. And so we have 4 oxygens, 2 CO2. So how's the rest of them carried? Well, great question. What happens is CO2 will come into the red blood cell. CO2 will mix with water. Carbonic anhydrase will push the reaction, and it will make H plus bicarbonate. Bicarbonate then will leave it and be transported within the blood. Once it's transported within the blood, then when it gets back to this point, it then comes back in. HCO3 minus. Then we'll come back in. Carbonic anhydrase will do the reaction. It'll push it the other way. CO2 then will come out and then be diffused out, and then we'll breathe it out. Pretty simple, pretty easy. Let me make sure I got everything with that. Discuss how CO2 are transported in the blood. Include description of how oxygen, hemoglobin factors into. Okay, yeah, and so this is kind of cool. So this is called the dissociation curve. So this is on the y-axis, we're looking at the percent of oxygen saturation. On the x-axis, we're looking about the partial pressure for oxygen. And so they're proportional to one another. So if we have a high oxygenation, we also have a high PO2. And so, but there are some things that can kind of change that. So hemoglobin itself, has an affinity to O2. But the affinity, it's not always, because if it's too high of an affinity, then O2 will constantly be stuck onto hemoglobin and it'll never be released. So there's some things that happens to allow this exchange to appropriately work. So a few things that can make hemoglobin hold on to O2 more or less is the partial pressure of oxygen, our pH, our partial pressure of CO2, temperature, and also this 2,3-BPG. This 2,3-BPG is super interesting, but basically what happens is it allows hemoglobin to either be more attached or less attached. So you can look here. This is called a right shift. And this is when we have less pH, more CO2, we have a higher temperature, and we have more of this 2,3-P DPG. And this DPG will make more of a T state. This T state is basically defined as when the structure of the hemoglobin and things like that, they have this, I call them like chopsticks almost, but they're basically electron clouds. And when you're in the T state, you don't allow oxygen to bind to the heme. So these are all the things that cause less oxygen to be bound to heme. And so a right shift will be more of a T state, which means less oxygen. And we can see that represented here. We have less oxygen saturation on this axis, which means we have less partial pressure of CO2. in each spot. When we have a left shift, we increase the pH, we decrease the CO2, and we decrease the temp. And this is more of an R state, which means more oxygen will be attached to heme, and more oxygen attached to heme, which means our hemoglobin, which I didn't say that. Excuse me, I'm hiccuping. This O2 saturation right here, this is how saturated it is within a red blood cell. That's what it is testing. This is like the pulse ox that you'd get when you go to the doctors, and that's what that's testing there. This is a real short one. We talked about the membrane, the pressures, the mechanism, negative pressure ventilation, pneumothorax. We talked about surfactant, and how surface area impairs ventilation. Well, actually, I'll talk a little bit more about. I did talk about it, but there's this pressure volume loop that I think is just cool so I want to talk about it a little bit more. So this pressure volume loop is it describes how much work it takes to get things done. So all of us have taken too many physics classes and too many chemistry classes, so I don't feel like I need to describe what work is more than just saying it's the amount of energy. So work is energy. And so when we're talking about this, it's how much work or how much energy. What is that? Oh, sorry. Welcome into my life. Anyways, so it's about how much work, and so this is taking in a breath. So when we're completely relaxed and we're all the air is out of our lungs, this pleural pressure is -3. As we inhale, we get this little bit of a plateau here. We're increasing pressure, but our volume doesn't increase much, and that's elasticity. And so we have to get over this elastic point, right? When you're squeezing, what are those, like workout grip things? When you're squeezing one of those, the hardest part is right at the beginning. And that's the same here. When you're breathing in, you have to overcome the most compliance. Once you've kind of broken through the level a little bit, you have to break through the most elastic part. Once you've broken through that, then it becomes a little bit more compliant, and that's when volume changes. And so we get up to about 15 millimeters of mercury. And then this is, this is inspiration. This is exhalation. And exhalation is kind of interesting because it also uses Clause's law, and it also uses surface area, and also uses radius, and all of those things. So for example, if we're thinking about this, so say our surface area increases, which means our lungs have a more difficult, we have less surfactants. Let's say that. We have an increase of surface area, which means we have less surfactants. If we have less surfactants, that means that this hydrogen bonding that's happening within this sac is more. So when we take this curve, it's going to come up and it's going to drop down really fast. That was like the exact same. It's going to come up the same, but it's going to drop down really fast because it's going to want to collapse faster. But say, for example, we have a super compliant lung. This is what our curve is going to look like. If we have a super elastic lung, this is what our curve is going to look like. So this thing measures pressure or measures work, and we can kind of assume that how much work it would take if we manipulate different variables, which I think is quite interesting. So we talked about that. We talked about Laplace's law. We talked about gas exchange. We talked about CO2 transported in the blood. We talked about hemoglobin. and the effects of oxygen on the curve. Yeah. So we got everything. It's a really quick and easy one, but thanks so much.